Now we'll see this problem. This problem is like this. So given a Turing machine ever moves its head more than 481 tape cells away from the left hand marker on input epsilon. So given a Turing machine, we should decide whether the Turing machine always moves its head more than 481 tape cells away from the left hand marker or not. For that we have to design the total Turing machine. So before going to designing total Turing machine, first we try to understand how to answer this question. How a Turing machine can compute that. For that we'll ask directly Raju. Raju, you are a Turing machine, your head is here. So rather than solving this problem for 481, we solve for 2 so that we can understand it easily. So the question will be, given a Turing machine, will it ever move its head more than 2 tape cells away from the left hand marker? This is more than, this is 1 tape away, 1 cell away, 2 cells, right, 2 tape cells. So more than 2 tape cells away means it should come here. Now we'll directly ask Raju. Raju, will you come here at any time? Then Raju says, I don't tell, because you have to find out the answer. Okay. Then what is the clue we have? We can run this Turing machine, right? But the only question is, we can simulate it. We have technique to simulate. Through the another Turing machine, we can run this Turing machine. But after how many steps we can decide? Example, we run only 1 step. Can we decide? No. Maybe 2 steps. Can we decide? We don't know. After 3 steps, we don't know. That's fine. Somehow if you can decide after some steps of running your Turing machine, Raju, if you can decide, then we can say it is decidable. That is the way we are planning now. We'll ask Raju, I'll run you for 5 steps. Okay. Please run for 5 steps and tell me what is your behavior. So Raju is running like this, 5 steps. Then after 5 steps you stopped and you said, see sir, I ran for 5 steps. After that, so after that also he is coming right side. Then I can say that, so Raju never comes, never comes this side. That's a false argument, because whenever you after giving this argument, immediately he might come here. Understand? So that's why we don't know. Maybe you have decided that with very few numbers of steps. Example, let's say you tried 100 steps. Sir, I tried 100 steps, but in this 100 steps, still Raju is moving here itself. Maybe after 100 steps he might come, correct? But definitely I am so confident that, so after some time we can tell it, because so he's not coming to this time. Without coming to this point, let's say he's only moving here, then definitely he will be in a loop. If you can find out a loop, then definitely we can answer. Don't worry, you can't understand completely, but slowly I will explain you. First of all, try to understand configuration. Assume that, let's say problem is to check whether Raju comes to 2 tape cells away from this left hand marker. That means will Raju come either here or here or here? That is the question. Let me number them. Tape cell 1, 2, 3, 4, 5. Will he come to cell 4 or cell 5 or so on is the question. For that what we do is, initially your tape is empty, see, on input epsilon. Okay, so that problem will be simple. Now assume that, let's say you have input alphabet only A comma B, tape alphabet also A comma B. That means only you have 2 symbols. Now assume that, let's say you have only 2 states. They are Q1 comma Q2 for simplicity. In the reality, depends on the problem, there can be hundreds of states, not a problem, right? Assume that for this simple problem there are only 2 states, Q1, Q2, and input A comma B. Right. Now the question number 1, I am introducing configuration. Configuration is nothing but, while running the Turing machine, I am taking a photo. If I click a photo, then you get some unique snapshot, correct? That snapshot is nothing but configuration. So that configuration tells you about, so where is the input output head, what is the state currently this Turing machine is having, and what is the tape configuration, tape pattern. Okay, now we'll see how many different tape patterns are possible for Raju. Okay, now initially all these are all empty, right? Now, so here I'm interested in knowing the configurations, but I want to know about configurations where your input output head is in this territory. That means it is only in these 3 cells. Okay, because I am solving a problem that whether my Turing machine moves its head 2 steps away from the input, left symbol, okay, left marker. That means, so I would like to know, without coming to this point or this point, how many configurations your Turing machine can make. Blindly, first of all, solve that. After that, we'll understand. Configuration number 1. Configurations are very easy to understand. Configuration number 1 is like this. I am listing out all possible configurations. Since we don't know, we don't really require about this remaining space, I show only this one, because what is interesting for you? Left hand marker, first blank, second blank, because this third onwards definitely they are blanks. Remember it. Okay, this is configuration number 1. I don't bother about remaining symbols because however they are all blanks only. Next, sir, these are all also blanks, right? But you are going to modify them, correct? Eventually, sir, but eventually I am also going to modify these symbols also, but for that your tape has to come there. But the question here is, I am interested in knowing how many different ways your Turing machine can run the code, but without moving its this tape right side more than 2 steps. Okay, so that's why, so don't move your tape more than 2 steps. We are not coming to here. When you are not coming here, then only you will be staying either here or here or here, then only these symbols can be modified. Then how many configurations are possible, we'll see. Configuration number 1 like this. Sir, it is not a complete configuration. Yes, correct, because state also important. When you are in this configuration, your state may be Q1, right? Anything else? That's it. Second different configuration possible, while reading this left hand marker, maybe you are in another state called Q2. Who knows? This is another configuration possible. Try to bring out other configurations. Sir, I know one more configuration. What is that? Why when you are in a state Q1, when you are reading the left hand marker, it is not initial configuration throughout the journey. Okay, so when you are in Q1, while scanning this cell, maybe these two tape symbols got already modified. Maybe in the previous iterations your Turing machine's head came here and it modified them. So that's why a comma blank also possible. Yes, let me list out all possible configurations. Left here, maybe same Q1 state, I can write AB. Sir, we are going to get so many configurations, it seems. Yes. Okay, let me confine my head to only first point so that we try to find out all possible configurations. So when you are in Q1, blank blank and AB, maybe BA, wide variety, correct? This is again left hand marker, and remember one thing, we never change this left hand marker generally, that is a custom. So anything else? Sir, BB. So lot of configurations, that's why, so I don't want to list out all possible configurations, but I will show some more configurations. One is left hand marker, maybe B, A, and your input head is here, or tape head is here. Yes, this is a different configuration than all these. Why? Sir, BA, sir, you have BA, right? BA, correct. Left hand marker, left hand marker. What is state? Q1, Q1. What is the difference? You are scanning this symbol, here I am scanning this symbol, so maybe I will be having a different step, correct? In that way, these are all possible configurations. Now without moving your tape head more than 2 steps, that means without coming here or here or here, by being only in these 3 steps, in these 3 cells, these are the configurations you can make. Okay, now assume that this is the first configuration. Okay, now interesting question, we will see that later. But when you are in this configuration, where can you go? Anywhere you can go. Tell me one possibility. It depends on the code. Example, your Turing machine's behavior is like this. Whenever it sees left hand marker, it will go to right side, let's say. That is a possibility. Then the step will be like this. It will go to a configuration called this one, left hand marker, blank blank. Okay, so it will come to Q1. So depends on your code, your Turing machine can come from here to here. Remember it. What is this configuration? Why you reached this configuration? Initially maybe you are scanning the left hand marker and you have decided to, maybe you have this type of move. I'll show it. That step is like this. Maybe your code is having like this: Q1 on left hand marker, go B in Q1 state, move right side and don't touch it. So that is a step. Sir, why this step is compulsory? No, this is one of the possibility. If your code contains this step, then you will be coming from this configuration to this configuration, you see. left hand marker is left hand marker, and we are moving the pointer to right side, then it will come here, then that's it. Q1 state is Q1 state. In that way, so we move from one configuration to another configuration, depends on your running code. Understand? See, without moving read write head more than 2 steps, how many configurations are possible? That is important for me. Okay, so let me calculate that. This is your semi-infinite tape, let's say. So in this semi-infinite tape, you have, let's say, left hand marker followed by cells, right? Now, initially all are blank because you are reading epsilon input, all blanks. The question is, how many different configurations are possible for any Turing machine without moving your tape head to more than 2 steps? That means initially it is here, then your tape pointer should be confined to only up to this area. We should not go to this area. So that's why it is always blank. Then all configurations are depending on this tape pattern, correct? So how many different ways you can change this tape pattern, so changes the configuration. Now we'll see. Since we are not disturbing these things, so how many configurations are possible? Configuration number 1. So here let's say assume that first of all number of states are 2, Q1 comma Q2 for one of the possibility. So for simplicity, let me take only 2 tape symbols. One is A, one is B. Even A comma B are part of input also. Assume that let's say blank is one of the tape symbol. A comma B are input symbols, blank is a tape symbol. Now states are 2. Now how many different configurations are possible for your Turing machine where your pointer is definitely not moving more than these 2 cells? Then one of the possibility, I show some of the things. Okay, one is like this. Since we cannot change the left hand marker, remember we never change that left hand marker. So one possibility is writing AA. Second possibility is fixing AA like this only, but by moving the pointer here and keeping pointer here. Second possibility. These 2 are different. Ask yourself why these 2 configurations are different. Now, sir, can you please show the remaining tape? All blanks. That's why I am not showing that, because that is fixed part. But only variable part is, so we are going to move this place, I mean we are going to move this symbol, and we are going to move pointer to here or here or here. That's why these 3 bits are important. Now anything else? Sir, I keep left hand marker but I write AB. Correct? Yes. So many different combinations are possible. How many such configurations possible? If you want to know the number of configurations, let me first of all see the variations in your only pointer, but everything is same. That means how many different ways you can change the head, that I am going to calculate. 1, right? Fix everything. State, let me fix to Q0. By fixing the state, by fixing the tape pattern, by fixing, that's it, by fixing that too, by only changing your tape head, how many different ways we can move, we will see. So this is second configuration, but state is same, Q0. Third configuration is left hand marker and AA fixed and Q0, but this time pointer is here. Only 3 configurations are possible for your pointer. Why? I mean by changing only pointer. Agree? Yes. Sir, why can't you move here? If I move it, then we are violating our rule. We are seeing the configurations where the pointer is not moving more than 2 steps right side. Okay, so 3. So it is very easy to understand because there are 3 positions to keep the pointer, so that's why 3 ways. Now how many different ways you can change the state, we will see. I fix everything same, but I only change the state, then it would be Q1 Q1 Q1. So don't change other things. That means left hand marker AA, right here left hand marker AA, I don't change anything other than state. So here Q1, correct? So I took Q1 Q2, I'm sorry, let's take it this as Q1, this as Q2, Q2 Q2 Q2. Okay, but remaining everything is same. Now slowly you will realize that how many configurations possible depends on how many different ways you can keep this head, how many different ways you can change the tape pattern, how many different ways you can change the state, correct? Now individually we'll see. First question, how many ways you can move the pointer? 3 ways. Okay, now how many different ways we can change the state? Either you can have Q1 state, Q2 state, 2 ways. So this is about state. Now third question, how many different ways we can change the tape pattern. Since we cannot touch the first bit, then how many different ways we can change this tape symbols? See here, you have only two other positions. This is fixed. We have only two other positions. Here you can write AA, AB. In combinatorics I taught you, when given two positions, in each position you can write A or B or blank. Then three ways we can fix the position. Then the total number of ways of fixing is equal to 3 into 3, 9. So 9 ways we can have a tape pattern, 3 square. Now the total number of configurations depends on this, right? It is like asking this question. Raju has 3 caps. Raju has 2 shirts. Raju has 9 jeans. Then how many ways he can wear one shirt? Simple. He will fix a cap. He will fix a shirt. He will fix a jeans. How many different ways he can do that? Product rule. 3 into 2 into 9. Correct? You understand that. In the same way, the number of configurations are 3 into 2 into 3 square. Remember it. Where 3 represents what? Number of, number of your read-write head movements. Second one. What is this 2? Number of states. What is this 2? This 2 represents number of these other cells other than left hand marker. Okay, first cell, remaining cells. So this 2 is linked to this 2, 481. Now what is this 3? 3 is about how many different ways each cell can be modified. 3 ways, because there are 3 tape symbols. This is number of tape symbols. Remember it. Now sir, why are you counting all these configurations? We did not understand anything. Yes, I know. But first you should understand that the number of configurations are 3 into 2 into 3 square. Remember it. Okay. Now I am erasing all these configurations. Let me focus on only one configuration. That is initial configuration. I show initial configuration. What is that? Left hand marker here and initially blank and blank, right? Remaining thing is as it is. Now initially state, will assume that Q1. Okay, this is your state and pointer will be here. Correct? This is the configuration number 1. Let's call. So from configuration number 1 to, let's say it is going to configuration number 2. And what could be the other configuration possible here to move? What is a valid configuration to which we can move? Tell me one possibility. Sir, one possibility going right. Then your pointer comes here and changing the tape symbol A. No, we don't change, right? Sorry, because so we are not reading this one. We were reading this one. So however, we cannot change that. This will be as it is. This will be as it is. Correct? But we can change the state. So in that way, from configuration 1 to we can come to configuration 2. Similarly, from configuration 2 we can go to another configuration. Let me show that. So what is that configuration 3? Tell me one possibility. So don't ask me, sir, why like this? Why not in other way? Yes, other way also possible, but I am taking one of the possibility. So the third configuration possible is, this time I would like to go right, but I want to change the state. If I change the state, I will go to Q1, and if I change the if I move to right side, I will come here, and I want to move it. I want to change this symbol to A. Yes, you get this configuration. So what I want to say is, all these configurations are already counted. They are part of this number 3 into 2 into 3 square. So 9 2 is 18, 3 is 54. There are 54 configurations. All these configurations are some of them. Now, what I want to tell you is here, initially when you started at configuration number 1, then you can go to configuration 2. After that maybe configuration 3, then configuration 4. In that way, you should move from one configuration to another configuration. Sir, I want to make a self loop. Is it possible? That means after one step you want to be in same configuration. Not possible, because at least that head should move left or right. Correct? When you move head left or right, then you are forming a different configuration. That's why definitely. So, and already I told you in the introduction that generally when we discuss Turing machines, we don't allow stalling. That means your pointer cannot stay in a in a same place. It should move to right or left. Correct? That's why from C4 we go to C5. Then what I want to say is, just closely observe for some point of some time. So initially C1, C2, C3, C4, C5. Now definitely there will be a loop. Why, sir? What if it goes to, because there are 54 configurations where your tape pointer is not moving more than 2 steps ahead. Correct? Sir, there is a configuration where your tape is moving to this point. Yes, but if it moves, that is a separate story. Without moving, how many configurations are possible? Only 54. Okay. Now, what is my question is, just run your Turing machine for 54 steps from start. If you run for 54 steps, then the possibility is, so if every time if your Turing machine goes to a different configuration after 54 times, let's run one more extra time, 55 times. If you run 55 times, either your Turing machine should go to a different configuration than this, otherwise it should repeat something else, correct? Because there are only 54 different configurations. Then if you run your Turing machine for 55 steps, then it should make a loop. Why? If it won't make a loop, then it should go to a different configuration. So according to pigeonhole principle, when you have only 54 different configurations, if I run 55 steps, since every time we have to go to a new configuration, then definitely we will go to a configuration which is not part of these configurations. Otherwise we will loop. Okay. Now what is my suggestion is, run your Turing machine for 55 steps. Okay. Then if within 55 steps, if it makes a loop, okay, example, let's say after 4 steps it makes a loop. One of the possibility, 1, 2, 3, 4. The fifth step is, let's say, loop, repetition. That means if it is going from configuration 5 to configuration 2, okay, then definitely next time it will come to configuration 3. Why? Because configuration 2 is fixed. That means whenever you are in this configuration, remember one thing. That means we are reading same. See, initially when we were at configuration 2, we were having this tape pattern, left hand marker, blank, blank, correct? And state is Q2 and pointer is here. Second time when you come to same configuration, then all the situation is same, environment is same, again same tape pattern, again same state, then you again will go to same C3, correct? Now I will give you one analogy. Example, let's say there is a loop, otherwise let's say you are visiting some new city, there is a circle, in that circle there is a right side, there is a hotel, but nothing is changed, it's a configuration. What happened? Let's say you are visiting this city. First of all, you came to this place, this circle, and just you looked around. Then you have seen a hotel right side. Then after some point of time, you came back. But this time, everything is same. That means no one has modified the construction. Then again you will come to same place. Let's say if you come one more time to same place, if you see right side, what you do? What you will see? Hotel, right? In the same way here also, when you come to configuration 2 again, what is the input you are seeing? This one, the tape symbol, correct? What is the state you have? Q2. So when you are in a Q2 state and the symbol is same, then decision is again same, correct? Such a way Turing machine is designed. Q2 blank, then there will be only one move, then again we'll go to C3. So what I want to say is, my dear student, whoever watching my video, run this Turing machine for 55 steps. If there is a loop, then your Turing machine never goes out of these configurations. It will be looping here forever. It won't make a new configuration. After 55 steps, if there is no loop, then all the configurations will be exhausted. Then it should go to a different configuration which is not part of these configurations. If any configuration is not part of this 54 configurations, then on that your IO, this head is there, right? Read and write head. Definitely it should be either here or here, because if you have head here or here, then the configuration will be part of this 54. Then definitely the remaining configurations are having, your read and write head outside the 2 steps. Now come to question. Given a Turing machine, you would like to know whether that moves its head more than 2 tape cells or not. Then for that, calculate the configurations. Now, if the number of configurations possible with these 2 tape cells and left hand marker is 54, run your Turing machine for only 54 steps. After, otherwise more than 54 steps, let's say 55 steps. After 55 steps, if your Turing machine makes a loop, Okay, we can construct this configuration, not a problem, correct? So if your Turing machine makes a loop, then you say simply there is, so it ever moves. So we can say that your Turing machine never moves out of this, two tape cells. And if there is no loop, then definitely it is going to outside after 55th step, correct? Then we can say that your Turing machine is going outside. In that way, whether your Turing machine is going outside at any time can be decided after 55 steps. Understand? That is what the concept. It is very difficult concept. That's why it takes lot of time to understand. Have patience and slowly understand it. Now let me tell you, otherwise let me consolidate it. Finally, first of all, calculate all possible configurations. They are finite. Forget about numbers. There are only finite configurations where your tape head is going to stay in this in this particular area. So after some point of time, after some configurations, definitely either it will loop, otherwise it will go out of that configurations. For that there will be some particular number. So run your Turing machine for that particular number. Example, in this problem 54 configurations. After 54 steps, either it will loop, either it will repeat the configuration, otherwise it will go out. That's why my suggestion is run your Turing machine for 55 steps. You can decide either that or this. Okay, so let me solve this bigger problem. What is our bigger problem? Now problem is not about two tape cells, correct? So the problem is about general Turing machine. You have a Turing machine, so it is going to have let's say initially left hand marker. There are k tape symbols. Okay, let me take k tape symbols and n states for this problem. Just who gave these values, I am assuming. Now the question, I want to check whether this given Turing machine ever moves its head more than 481 tape cells or not. Okay, now you do one thing. First of all, calculate the number of configurations. How many different configurations possible where your head never moves more than 481 steps? This is after 481 steps. Okay, if in how many configurations your Turing machine's pointer is going to stay in this first 481 cells? For that, definitely formula will be, did you remember, for two cells. So first of all, we'll see how many different positions this can point. First we see that. First possibility is to find out the configurations. This is left hand marker. So from here, your tape head should not go more than 481 tape cells, correct? See, it cannot go more than 481. Let's say these are all 481 tape cells. Okay, other than this one. So your Turing machine can go up to 481 tape cells other than left hand marker. Then finally, how many cells we have? 482. Then how many different ways we can arrange this pointer in 482 cells? 482 ways. So 482 ways we can arrange the pointer. Second, how many states we have? N states. Then how many different ways we can change the state? N ways. Then how many tape symbols we have? K tape symbols. Then each position other than first position, in every position can be filled in how many ways? K ways. How many such tape cells we have? 481. So K into K, how many times? 481. K power 481 tape patterns are possible. Finally, number of configurations are 482 pointer configurations into n state configurations into K power 481 this cell configurations, correct? Finally, it will be 482 into n into K power 481. So run more than, that means more than these many steps. If you run more than these many steps, then either your Turing machine pointer will go out of this 481 tape cells, otherwise after these many steps also still it is there in these configurations only, then it is going to loop. In that way always we can decide it. That's why this problem is decidable, because to answer this problem we have algorithm, we have a systematic procedure. It is going to terminate after how many steps? 482 into n into K power 481 steps. That is important, and don't memorize it, not required it. Okay, understand the concept. right? And one more time I'm telling, this concept is very difficult. So many people, like, no institute generally teach about these concepts. Okay, one thing. Second one, why? Because it is very difficult to explain to the students. That's why. But I'm going to explain you. I'm explaining also, of course, but that's why. But definitely you face a difficulty. Whenever you face a difficulty while watching this lecture, it's a part of the game. Understand it. Okay. So it's not because of your understanding. It is for everyone. Everyone will face difficulty in understanding disability. So 95% of the students are going to skip this part. But you are watching the lecture means you are putting effort to understand these lectures. It's good. But definitely your brain will stop you, but still have patience and try to understand every bit whatever I am teaching, so that definitely it will help you. Okay, but one thing, if you don't have time, then don't watch, because you have to write the gate exam in time limits, right? So if you want to read some important topics, please complete them. If you don't have any important topic to complete, already you have covered all the syllabus still, but you want to learn new things and difficult things, then this is for you. Okay.